I'm Iatchenii. I'm a regular contributor of KLEE, and today I'm looking forward to talking with you about crucial problem in computer science, namely undefined behavior. We will cover some approach to tackle with that using KLEE and introduce new one based on my work. So let's get started with the definition of like this. Okay. Let's get started with the definition of undefined behavior. Firstly, this is not unspecified behavior for which the language standard doesn't prescribe a result at all. Secondly, this is not implementation behind behavior that differs to the specification of another component of platform. And also, C language standard gives a definition which is quite difficult to understand. And paraphrasing this, C community gives an alternative definition which literally says that anything at all can happen, the program may fail, and so on, so on, so on. So by default, KLEE covers some cases of undefined behavior. First and foremost, it injects checks into bytecode for division by zero and overshift overflow. Next, it handles some cases naturally during computation, for example, for dereferencing a null pointer. However, there are some cases that are hard to catch without instrumentation of source code, for example, integer overflow, and it will be shown in the following examples. On the left-hand side, integer overflow gets missed. It is clearly undefined behavior, but compilation and calling this function with symbolic argument doesn't produce error tests. On the right-hand side, implicit conversion from integer type to char type with data loss gets also missed. This is not undefined behavior, but often unintentional behavior and may also be a bug. So to address these issues, LLVM Undefined Behavior Sanitizer can be used as a basis. It consists of two parts. The first part is code generator or just compiler, which uses compiler time instrumentation to insert checks and handlers. And the second part is runtime, which implements those handlers and exits the program. We decided to use LLVM code generator as this. I believe that LLVM has very smart checks and we can do any better than that. And to exploit these features, just adding flags to clown compiler is sufficient. And you get your bytecode instrumented. And it's also necessary to turn adopted LLVM runtime to our own KLEE library runtime. And it makes possible to analyze data and report error tests. So let's get back to the example of inaccurate absolute function. By default, if you compile this code, the resulting bitcode doesn't store information about signedness, and it makes it almost impossible to detect undefined behavior. However, once your code is instrumented with LLVMSanitizer, the negation instruction is replaced with checked instruction, and handler starting with underscore prefix. So yeah, this and many other handlers have been implemented by me. For example, consider a common diagnostic mission which reports error tests and gives some useful information about it, and particular handler for negation overflow as in the example above. So as a result, with this extension, it makes such issues easier to diagnose and troubleshoot. This extension was successfully tested on almost all available checks of LLVM or symbolic and concrete values. And In addition to that, it's actively used in UTBot CPP unit test generation tool. You may find out more information about this in other presentation today. And that's all for me now. You can explore more about contribution, sanitizer, and unit test generation tool following these links. Thank you.